Hey everyone, welcome to Lecture 1B. We're going to get started by doing just a couple more examples of rational functions. Then we're going to move on to a quick refresher of derivatives. Then we'll use first and second derivatives to help us more accurately graph functions. After that, we'll finish with a review of partial fraction decomposition. All right, let's get started.
Okay, so now we're going to try to graph this function. And something that distinguishes this function from the functions that we looked at yesterday is that it is not factored, right? Yesterday, most of the functions that we looked at were partially or almost fully factored, which meant that it was pretty easy for us to tell if any of the factors were going to cancel. In this case, we can't tell that at all until we fully factor the numerator and denominator. So we're going to refrain from trying to figure out what the roots and asymptotes are until we factored both of the numerator and the denominator completely. So let's go ahead and factor the numerator. So that's x cubed minus 2x squared minus 4x plus 8. There should be basically three methods you know to factor cubics. One of them is the sum of perfect cubes, one is the difference of perfect cubes, and one is factoring by grouping. This is going to be factoring by grouping, but if those other methods sound a little unfamiliar to you or you don't remember the details of the formula, you should probably look that up now or after this video, just in case it comes up later. But in terms of factoring by grouping, that means we're going to look at these terms as pairs, and we're going to find the greatest common factor of each pair. So between x cubed and negative 2x squared, I can pull out an x squared, and that leaves me with an x minus 2. And then between negative 4x plus 8, I could pull out a 4, but I always want to match the sign of the first term there. And since that's a negative 4, I'm actually going to pull out a negative 4. And that'll leave me with x. And if I pull a negative 4 out of positive 8, I'm left with a negative 2. Then the factors I get, one of them is going to be that factor that I have in common there. So that's at x minus 2. See, we have it after both of these. If I had something different after both of these, that means that my factor by grouping did not work. So we probably have to use some other method. We're generally not going to give you functions like that. We have to use another method. Really, the only next option is to figure out what a root is by plugging in numbers and then doing like synthetic division or polynomial long division to get the quadratic, which you can then factor. So this is one of our factors, and the other factor is going to come from those coefficients, which is x squared minus 4. And that is a difference of perfect squares. So that is going to be x minus 2 times x plus 2. And now we have all those linear factors. So our denominator is fully factored. I'm sorry. So our numerator is fully factored. And now let's do our denominator. So x squared plus 5x plus 6. And that is going to be, we're looking for two numbers that multiply to 6 and add to 5. So that's going to be x plus 3, x plus 2. So the denominator is fully factored. So let's write this function as, so let's give this function a name really quick. So let's call this f of x. And we're going to say f of x equals x minus 2, x minus 2, x plus 2 over x plus 3, x plus 2. And notice that we have an x plus 2 in the numerator and denominator. So we could cancel those out, sort of. And so we're going to say that it equals, and I'm putting that in quotes. So x minus 2, x minus 2, x plus 3. And we're going to call this thing on the right g of x. So in theory, these should be the same. And they are for almost every input. But there's one input that's not going to make them the same, and that is the input that makes the factor that we canceled out be 0. So notice that we canceled out that x plus 2, which would be 0 if x was minus 2. And I went ahead and I plugged minus 2 into f of x and minus 2 into g of x here. And so you can just pause the video and check through these details to see what I did. I just didn't want to go through the tedium of doing that live. But we see that when we plug negative 2 into f of x, we're going to get 0 over 0. And when we plug negative 2 into g of x, we're going to get 16. And so those are not the same. And I want to quickly look at Desmos to see what Desmos does in this situation and how these two functions differ. So over here on the left, I have f and g. And if I show g, we see that it lines up perfectly with f, right? So it looks like they're going to be equal everywhere. But I just want to zoom in really close here to right around -2 and watch as I slide along here. Notice that the little dot it makes is filled in. But when I get right to -2, it changes into this open circle, right? So we have this open circle and it says -2, comma, undefined, right? That means that essentially -2 is not even in the domain of our function f, right? Our function is not defined on -2. We just removed that from the domain. But then let's look at g of x and let's see what this looks like. And let's follow this along. Let's see if we can get it to exactly -2. It's a little bit hard to be that precise with the mouse, but okay. And notice that here we have this filled in circle and it says -2, comma, 16, right? So g of -2 is 16 and f of -2 is undefined, just like we saw in our computations. So what is our conclusion that we can kind of draw from this situation? Well, that is that essentially cancellation creates holes. So we have that written right there. The caveat here is that we only create holes when the factor cancels completely, which means that there's no copies of it in the numerator or denominator after canceling. So I have a couple examples here, and let's look at this first one. So in this first one, we get a complete cancellation here. So this is going to have a hole at x equals -2. Let's look at the second one. Well, the second one, we have a x plus 2 cubed in the numerator and an x plus 2 squared in the denominator. So we're left still with 1 in the top. So there is no hole, but there is a root at x equals -2 with multiplicity 1. And then let's look at this one. Well, now we have a cubed in the bottom, so we lose all of them in the top, but we still have 1 left in the bottom. So once again, there is no hole, but there is an asymptote at x equals -2 with multiplicity 1. That was a little diversion, but let's go back to our function now, our f of x. And so we're going to try to graph f of x by using what we know about g of x. So because we know that g of x has the same shape as f of x, right? As long as we keep track of that hole that we have to draw, everything else is going to be the same. So we're essentially just going to look at this function that we have here, which is x minus 2 squared over x minus 3. Okay, so now let's think about the normal things that we do when we try to graph a rational function. So let's look at end behavior. Okay, and so we're going to say that that is like x squared over x, which is x. So that looks like this. Then we could look at the roots. So now we have x minus 2 squared equals 0. And notice, I do want to point this out once again, because this is important, is that we had to make sure we factored everything and canceled before we found the roots. Because if I just started with my original function and I said, I'm not even going to think about the denominator, I'm going to factor in the numerator and find the zeros, I would have found a 0 at x equals -2, but there isn't one there because it canceled from something in the denominator. So we have to make sure we factored everything first and canceled, and then we're going to revisit the numerator this second time to look for the roots. Okay, so this is where we have x equals 2, and that has multiplicity of 2. Look for asymptotes. Actually, I miscopied this before. That should be a plus in the denominator. So that is going to be x plus 3 equals 0. So x equals -3, and that has multiplicity 1 because that just raises the first power. And now we can go ahead and try to graph this. So let's come up with a suitable scale. We'll go -1, -2, -3, and we're going to put an asymptote right here. let's see what else we have. So we have a root at 2 with multiplicity 2. So we have a root here. We have this end behavior that looks, it goes up over here and it comes down over here. And the other thing that we can't forget is that we have a hole, like we just found, at -2, comma 16. So, oh gosh, what do I want my scale to be here? Let's go to, yeah, I'll count by twos. So I'll make this 4, 8, 12, 16. And so our hole is going to be -2, comma 16. And I'm going to draw that as an open circle. Okay. So I'm going to start over here at this end behavior. And I can't cross the axis because then I would have a root that I haven't found. So I have to go down this asymptote. And that is an asymptote of multiplicity 1. So we do opposite things on either side. So we're going to come from the top over here. We're going to go through this hole. And then we're going to come and we're going to touch the axis right here because that's multiplicity 2. So it kind of looks like a parabola at that root. And then we're going to come back over and meet our end behavior there. Okay, so let's kind of see how that matches up with this graph, which we did just look at. Yep, basically what we drew, right? So we come up and then we go down and then we go through the hole and bounce off and back up. Now let's look at our chart of end behaviors that we had from last time. And I'm going to take a look back at Desmos, looking at this graph that we just looked at. And let's think about what happens if I change this x squared to an x cubed. So now if we do this sort of end behavior analysis that we've been doing, we're going to say that this is like x cubed over x cubed. And notice that that isn't x to some power and it's not x to some negative power, right? Because this is actually just a constant. And we didn't include that in our chart, right? Notice we're saying that it's either x to something bigger than 0 or less than 0, but this is actually x to the 0 power. And so this is the last thing that we have to consider. And we're going to add this to our chart in a second, but we're just going to look in Desmos for a second to kind of conceptualize why it works the way that it does. So we're saying that this is, right, essentially like -3 over -3. And so that's like the function x cubed over x cubed, which is really just the function 1, y equals 1, right? And so we see that it approaches this line, right? It approaches this constant function as we approach positive or negative infinity. Okay, what if in the top we had a 4? Okay. So then now this is going to be like 4x cubed over x cubed. So that's going to be like 4. So that's going to be y equals 4, right? So we get an asymptote at y equals 4. What if in the top we had a negative, let's say -9, and the bottom we had 3? So that would be like having a -9 here, having a 3 in the bottom. And when we divide that, we're going to get -3, right? So essentially our rule is that when we have the same leading power or the same degree of polynomial in the numerator and denominator, then we're going to have what we call a horizontal asymptote at the quotient of the coefficients, right? And a horizontal asymptote is essentially a type of end behavior. And so that's how we're going to think about it here. So we have here, like I just said, when the numerator and denominator have the same degree, then it's going to look like this: ax to the n plus blah, blah, blah over bx to the n plus blah, blah, blah. Then our end behavior is characterized by the horizontal asymptote y equals a over b, right? And that's just going to be some number because a and b are numbers. So our end behavior type is essentially what we're going to call x to the 0, right? Which is, it has some coefficient c there. like we were just doing in Desmos, which is the same as saying just C because x to the 0 is 1. And what that end behavior is going to look like is we're just going to have, it's going to be some line here. I'm going to just approach some line. I'm going to draw it as a dotted line here. And I'm just going to show that we're kind of on that line off towards the ends there. Of course, we never necessarily actually reach the line, but we do approach it and get closer and closer. So it's going to sort of look like we're on that line. Right, and that line specifically is at whatever our value of C is. And in this particular drawing I drew, it looks like C is going to be a negative number. So let's just do one example really quick with the horizontal asymptote. Okay, so let's start by looking at the end behavior. So we're going to say it's like x squared over x squared, which is 1. So we're going to have a horizontal asymptote at y equals 1. Now remember, before we do roots and vertical asymptotes, we need to factor the numerator and denominator. So we see that our h of x is going to be x plus 3, x minus 3 over, let's see, things that multiply to 12 and add to negative 7. So that would be x minus 4, x minus 3. And now we see that we do get these canceling out here. So that's going to give me x plus 3, x minus 4. But we do want to note right now, because we canceled out that negative 3, that we're going to have a hole at 3, comma, and then we're going to plug 3 into this. So it's going to be 3 comma h of 3, and h of 3 equals, and I'm just going to plug it into that, what do we have there? So it's 3 plus 3 over 3 minus 4. So it's 6 over negative 1, which is negative 6. So hole is at 3, negative 6. Okay. And so now we can go ahead and find the roots. And this is really easy. So we just have x plus 3 equals 0. So x equals a negative 3, multiplicity of 1. And then the asymptotes. And when I say asymptotes, I always mean vertical asymptotes unless I specify. That we get from x minus 4 equals 0. So x equals 4. And once again, multiplicity 1. So let's go up here and graph this using all the information that I know. So let's first put the hole on here. So that is going to be 3, negative 6. So that's 3, negative 6. And I'm going to do that as an open circle. Then our end behavior is the line y equals 1. So I'm going to draw that as an asymptote right here along y equals 1. We have a root at x equals a negative 3. That's going to have multiplicity 1. And we have vertical asymptote at x equals 4. And that also has multiplicity 1. Okay, so what's this going to look like? Okay, so we know that we have this end behavior like this. So I'm going to kind of just start by following this line more or less. And then I have this root here. So I'm going to go through that root. And this is actually a case where it might be useful to find my y-intercept. So let's actually just do that really quick. So I'm noticing I don't quite know where to pass through that y-axis. So let's just go. Okay, so we're just plugging in 0. So it's going to be 0 plus 3 over 0 minus 4. So that's 3 over minus 4. So that's a negative 3/4. So actually, so that's like right here about. Which means that our scale is a little weird, but it's okay. So we're going to go here, and then we're going to pass through this point here. And then we're going to come down this asymptote. And now remember, we have multiplicity 1 on this asymptote, so we do opposite things on both sides. So we're going to come up on this side, and then we have to go and approach this asymptote over here. Okay, so this is our attempted graph. Let's look at it in Desmos. So our function is x squared minus 9 over x squared minus 7x plus 12. We said that our asymptote was going to be here, and that looks to be right. Also, our drawing looks essentially like what we drew here. And we said that we should have a hole at 3, -6. And let's see if Desmos agrees. So we're going to go try to follow this along. And there we go. There's our hole. So that looks good. Okay, now we're just going to do a really quick review of derivatives. I'm just going to run through these derivatives and just do them, kind of refresh you. If this is looking like something that you feel a little bit rusty on, you definitely want to like go through this chart, maybe do some flashcards or something, because we're definitely going to be using derivatives basically every day of this course. So, okay, let's go ahead and, so I have 7x, derivative of that is 7. X squared, I'm going to pull that 2 out in front, we get 2x. X cubed, we're going to pull a 3 out in front, and then I'm going to reduce the power by 1, I'm going to get x squared. This is supposed to be an n, make that a little bit clearer. Okay, so this is just to generalize what we did above. If I have any n, I just pull the n out in front, and then it's x to the n minus 1. Notice this rule only works when my base is the variable that I'm differentiating with respect to, and the power is some constant, n. Okay, so if we have e to the x, the derivative of that is e to the x. What about 2 to the x? That's 2 to the x times ln f2. What about n to the x? So, right, this is different than the one above because here we have x in the exponent. And so this is going to be n to the x times ln of n. Derivative of ln of x is 1 over x. Of sine of x is cosine of x. Of cosine of x is negative sine of x. Secant of x is secant of x times tangent of x. Derivative of tangent of x is secant squared of x. Derivative of arctan of x is 1 over 1 plus x squared. Derivative of arc cosine is negative 1 over the square root of 1 minus x squared, and derivative of arc sine is 1 over the square root of 1 minus x squared. All right, those are some of the most important things that we need to know. Let's go on to our derivative rules. So chain rule, the derivative of some composition of functions, so f of g of x, we're going to start by just taking the derivative of the outer function and just plugging whatever we had inside into that. And then we're going to multiply that by the derivative of the inside. And we could keep doing this again and again and again. So maybe I'll just kind of write like d dx, if I had f of g of h, then I want that to be a function. So of h of x, okay, close my g, close my f, close my braces. So that would be f prime of g of h of x times g prime of h of x times h prime of x. Now this is maybe a little bit abstract, and I think it'll be pretty clear how this works with our examples here. So let me just kind of push that over. So, okay, cosine squared of x, we want to think of that as being, now equals doesn't mean derivatives, it's just actually equal to. It's the same thing as saying cosine of x squared. And so when I take the derivative, we think of this outer function, like our f of x, as being x squared. And so f prime of that is 2x. So it's 2 times, but here our x is actually cosine of x. So it's 2 times cosine of x. And now our g of x is cosine of x. So what's g prime? Well, that's going to be negative sine of x. So times negative sine of x. Okay. And so I could rewrite that as negative 2 cosine x sine of x. And if you wanted, if you know your trig identities, that's going to be negative sine of 2x. Okay, e to the x cubed. So derivative of e to the something is just e to that same thing. And then we have to multiply by the derivative of x cubed. So that's times 3x squared. And it might be more conventional to write it like this. Okay, ln of secant x plus tangent of x. So derivative of ln of something is 1 over that something. So 1 over secant x plus tangent of x times the derivative of what's inside. So inside is secant x plus tan x. So derivative of that is going to be, so derivative of secant x is sec x tan x. And then the derivative of tangent of x is secant squared of x. And we could simplify this a little bit too, because the way I actually want to write this is with this in the numerator. So sec x tan x plus secant squared of x over secant x plus tangent of x. And we're going to notice that we can actually factor a secant of x out of the numerator. So we're going to do that here. So that's secant of x times, then I have a tangent of x left, plus then I have 1 secant of x left here over secant of x plus tangent of x. And then I noticed that tan x plus sec x, that's the same as sec x plus tan x. So that's actually going to cancel out. And so that is going to be secant of x. Okay. And here's going to be our last chain rule example. So if f of x equals this, then f prime of x equals, so derivative of sine is cosine of whatever we had inside. So that's of ln of tangent of e to the x times, we're going to move in. So now we're taking the derivative of ln. It's going to give me 1 over whatever I had inside. So that's tangent of e to the x. Moving in another step, we have tangent of e to the x. Derivative of tangent is secant squared. So that's times secant squared of e to the x. And then you have to move in one more step, and that's e to the x. And derivative of that is e to the x. So there's our derivative. Next, we're going to look at the product rule. So that is the derivative of f of x times g of x. And that is going to be f prime of x times g of x plus f of x times g prime of x. And I think it is somewhat common to write this product rule using u's and v's. So maybe you've seen this before, it written as d dx of uv equals u prime v plus uv prime, or some people write it as u prime v plus v prime u. So whatever, these all say the same thing. And let's do a couple examples of this. So our first example is x times ln of x. So we're going to say, okay, derivative of x is 1 times ln of x plus x times the derivative of ln of x, which is 1 over x. So that's going to give us ln of x plus 1. Okay. Our next example is cosine of x times e to the x. So derivative of cosine of x is negative sine of x times e to the x plus cosine of x times the derivative of e to the x, which is just e to the x. And so if I wanted to, I could factor out an e to the x, and then I'd have negative sine of x plus cosine of x. And I'm just going to rewrite that in the other order so I don't have to have a negative first. So there is my derivative. Okay. And now we're just going to talk about what derivatives mean. So remember that when a derivative is positive, it means that the function is increasing. And that should make sense, right? Because the whole point of derivatives is that the derivative is the slope of the tangent line. And if you have a positive slope, that means that you have an increasing function. So if f prime of x is less than 0, that means that f is decreasing. So if f double prime is bigger than 0, this is the second derivative, right? Which just means the derivative of the derivative. That means that f is concave up. And if f double prime of x is less than 0, that means that f is concave down. And now we're going to use this information to help us graph functions using their derivatives. Now let's try to graph the function f of x equals ln of x over x. So first, let's try to find the roots of our function. And when we have a fraction, we know that the roots of the fraction occur when the numerator is 0. So we're going to say ln of x equals 0. And the way that we cancel out an ln is we raise e to the power of both sides, right? So e to the ln of x equals e to the 0. And ln of x, right, is saying what power do I need to raise e to get x? So So by definition, e to the ln of x is x, and anything to the 0 except 0 is 1. So we have x is 1 for our roots. Okay. And now we want to find the intervals where our function is increasing and decreasing. So we're going to start by setting the derivative of our function to 0, but let's just find our derivative. So let's just quickly remind ourselves of the quotient rule. So if f of x is u over v, that means that f prime of x is u prime v minus u v prime over v squared. That means that our f prime of x here, f prime of x is, so our u is ln of x, so the derivative of the top is going to be 1 over x times the bottom, so times x. The way I usually think of this when I'm just writing it out, as I say, the derivative of the top times the bottom minus the bottom times the derivative of the top over the bottom squared. Some people like to say they say low d high minus high d low. So d meaning derivative, and high meaning top, low meaning bottom. Okay, so minus uv prime. So u is ln of x, and the derivative of the bottom, the derivative of x is just 1, and then over the bottom squared. So we have this. So that's 1 over x times x. That gives us 1. 1 minus ln of x over x squared. So in order to figure out where it's increasing and decreasing, we have to figure out the places where it can change sign. And remember that a function can change sign where it is 0 or where it has an asymptote, right? If I just let's just graph some random rational function really quick. And let's just think about, like, let's just say we had an asymptote there or something, and then we had a 0 there and some asymptote there, right? Notice that, so the sign changes at this point right here and also at this point right here. So it's not guaranteed to change at an asymptote. It's also not guaranteed to change at a 0, right? We could have a 0 where we bounce off. But we do need to check the asymptotes and the zeros because those are the places where we can have the sign of the function change. So let's go ahead and set the numerator equal to 0. So 1 minus ln of x equals 0. That gives us 1 equals ln of x. And e to both sides, so it's e to the 1 equals e to the ln of x. And typically I'm not going to write this intermediate step that I just wrote because we don't usually do that when we do algebra and with other things. So e equals x. All right, so x equals e. And then let's also set the bottom to 0. X squared equals 0 gives us x equals 0. Okay, so now that we found our possible sign changing points, we're going to draw a number line. And I'm just going to draw these points on the number line, 0 and e. I'm just drawing them in order, right? 0 is bigger than e. And now this cuts our number line up into 3 intervals, right? The first interval is -infinity to 0. Second one is 0 to e, and the third one is e to positive infinity. So we want to see if it's increasing or decreasing in each interval. And we know that it will do the same thing in each interval because it can't change unless it hits a 0 or an asymptote, and there's no zeros or asymptotes within each interval. So let's pick a number inside of our first interval here. So let's just pick, we know that 1 is in this interval, so I'm just going to stick a 1 there. What's a number over here? Maybe let's say -1. And what's a number bigger than e? I'm actually going to pick e squared, right? Because e is like 2.7, so e squared is bigger than e. Keep in mind that squaring a number doesn't always make it bigger, right? If I had 0.5, 0.5 squared is 0.25, which is smaller. Squaring a number only makes it bigger if our number is bigger than 1. Okay, so we have to test these points. So let's, in our derivative function, so 1 minus ln of -1 over -1 squared. And so ln of -1, what happens there? Well, it's saying e to what power gives us -1, but e to any power is positive, so we can never get -1. And so this right here, this is undefined. And so that means that everything is undefined, right? So in fact, anything less than 0, if we plug anything less than 0 into our function, we're going to get undefined. So that's not positive or negative. The function just isn't there. There's no graph of the function, right? Graph of ln of x, by the way. I think we did this yesterday, so we should kind of have some recollection of what this looks like, right? Just to kind of remind you, right? It looks like this. We have this asymptote here, and then there's nothing on the negative side. And I'm just going to erase that because not to confuse with the graph of this function. Okay, so now let's try plugging in 1. So 1 minus ln of 1 over 1 squared. Okay, so 1 minus, what do I have to raise e to get 1? Well, e to the 0 is 1, so that's going to be 0 over 1 squared. So that's, okay, so that's 1, right? 1 minus 0 is 1 over 1 is 1. And that the point is that 1 is bigger than 0. So this is a positive number. The derivative is positive, right? Which means that our function is increasing on this interval. And then let's try that last interval. So we'll say 1 minus ln of e squared over e squared squared. So that's 1 minus, what power do I have to raise e to get e squared? 2 over e to the 4th. And so that is -1 over e to the 4th. And so e to the 4th is positive, so it's a -1 over some positive number, so that's going to be a negative number. And so we're negative in this interval here. Okay, so let's just write down what we found. So we found that we are increasing from 0 to e and decreasing from e to infinity. What about at e? Well, at e, the derivative is 0, right? So we're not increasing or decreasing there. That's going to be, and think about for a second, is it going to be a max or a min? Well, we're increasing before, and then we're decreasing after. So that's going to be a maximum. If we were decreasing before and then increasing after, that'd be a minimum. So now we want to take the second derivative. So f double prime of x is the derivative with respect to x of the first derivative, and our first derivative is 1 minus ln x over x squared, which is the derivative of the top. So the derivative of 1 is 0. The derivative of negative ln x is -1 over x. So the derivative of the top times the bottom. So the bottom is x squared minus the top, which is 1 minus ln x, times the derivative of the bottom. Derivative of x squared is 2x, all divided by the bottom squared. Okay, so let's work on simplifying this a little bit. So in our top here, we have -1 over x times x squared. And so I can cancel out one of those x's, and I end up with just -x minus, I'm going to distribute, Leah, let me just first distribute that 2x through there. So 2x minus 2x ln x over x to the 4th. And now I'm going to distribute my negative sign. So it's -x minus 2x plus 2x ln x over x to the 4th, which is -3x plus 2x ln x over x to the 4th. And now I can cancel out one of these x's on the bottom. See, each term in the top has an x in it. So I can factor out an x like this, and I get -3 plus 2 ln of x over x to the 4th. So I can cancel this x with one of the x's in the bottom. And so we end up having -3 plus 2 ln x over x cubed equals 0. And now we can go ahead and set this equal to 0. So let's set the top equal to 0, because that's one way that we can get a change in sign is when we have roots. So -3 plus 2 ln x equals 0. I'll add 3 to both sides. 2 ln x equals 3. Divide both sides by 2. Ln x is 3/2. And so raise e to both sides, and we get x equals e to the 3/2. And then the other thing is if the denominator is 0, we have x cubed equals 0. And so x equals 0. And we kind of saw before that that's probably not going to help us too much because the left side of that is nothing anyway. So let's draw our number line here. We're going to put a 0 in. We're going to put an e to the 3/2 in. And then let's pick some numbers in here. So e is less than e to the 3/2 because it's e to the 1. 1 is less than 3/2. And because the e base there is bigger than 1. And we'll pick a number over on the other side, and I'm just going to pick e squared. So let's try plugging these things in to our second derivative. So it's -3 plus 2 ln e over e cubed. So what does that give me? That gives me -3 plus 2 times 1 over e cubed. So that's -3 plus 2 over e cubed, which is -1 over e cubed. And so that's going to be a negative number. Let's try plugging in e squared. -3 plus 2 ln e squared over e cubed. -3 plus 2 times 2 over e cubed. So that's a -3 plus 4 over e cubed, which is going to be 1 over e cubed. And so that's bigger than 0, which means that our second derivative is negative in this first interval and is positive in this second interval, which means that between 0 and e to the 3/2, we are concave down, and between e to the 3/2 and infinity, we're concave up. Remember that concave down is like this, is like an arch, and concave up is like a smiley face. I think I've heard some people say, you're feeling down, so you're sad. So it's like a frown face, or, I guess you're feeling up, you're happy, smiley face. So you can think of it like that too, if that's helpful. Okay, so now we've got a lot of information, and we're going to try to use this to draw our function or to graph our function. So I don't really care too much about my negative x-axis because nothing is going on over there. So what are our important points? So we know that we have the change in sign of our concavity at e to the 3/2, which we call an inflection point. And we have a change in point of the increasing decreasing at e, which is a critical point. So we'll label some points here on our axis. We'll just put 1, e is going to be around here, and then e to the 3/2, well, it should probably be around here actually. So I'm going to extend this a little bit further. And okay, so remember that we have a root at 1. We're going to have our critical point here. And so we said that from 0 to e, we are going to be increasing. From e to infinity, we are decreasing. And then from 0 to e to the 3/2, we're concave down. And from e to the 3/2 to infinity, we're concave up. So let's see what we can do here. So we know that we're increasing here. We're also undefined to the left at this point. And we're going to keep increasing until we get here. And we also know that we're concave down, right? And we have to kind of stay with this direction of curvature until we get right here. And that means that once we get here, we can start to be concave the other way. So let's actually I just want to draw a couple pictures concave down. So concave down could look like this, right? Or it could look like this. And concave up could look like, it could look like this, or it could look like this, right? So it has nothing to do with if we're increasing or decreasing. It's just about, sort of if it looks like a piece of a bowl or a piece of a dome. Let's have a quick look at what this actually looks like in Desmos. All right, and here we are. So we have this x equals e right here, and that is where we reach our max and change from increasing to decreasing. And then we have this black line here, which is e to the 3/2, and that's where we change from being concave up to concave down. And you can sort of see, it's a little hard to see exactly without the line there where the concavity changes, especially because near the point where the concavity changes, we're a little bit more linear. But I mean, that sketch looks essentially like what we drew. Notice that the scale here is really uneven. So that's why it looks a little bit more compressed than what we drew. But I find that this scale makes it slightly easier to see the concavity, and that's why I used it. A common question you might be asked about graphs like this, and that perhaps it would have been helpful to have figured out before we tried to draw the picture, is what are the critical points and what are the inflection points? So that's a word that I mentioned. And we know that the critical point occurs when x equals e, and the inflection point occurs when x equals e to the 3/2. And then all we need to do is just plug that first number into our original function. So our original function, remember, was ln of x over x. So if we took ln of e over e, that gives us 1 over e. And for our second one here, we have ln of e to the 3/2 over e to the 3/2, which is 3/2 over e to the 3/2, which I could rewrite because we don't really like to have fractions inside of fractions as 3 over 2e to the 3/2. Okay. And now if we wanted to, we could label, for example, this point, which is supposed to be our maximum here, as e comma 1 over e. And we could label this point as e to the 3/2, 1 over, what did we say it was? 3 over 2 e to the 3/2. And in some situations, it might actually be really helpful to figure these out first, just to give us some anchor points that we want our graph to go through. I think in this situation, it's maybe not particularly helpful because it's hard to even know numerically in our head what number 3 over 2e to the 3/2 is. The next thing we want to try is to graph the function n of x equals e to the negative x squared. And there's a reason I used the letter n, but I don't want to tell you because it's a spoiler for what the function is going to look like. Let's start by looking to see if we can find any roots. So that says that e to the negative x squared equals 0. But that would mean if we tried to take ln of both sides, we would get negative x squared equals ln of 0, which is undefined. So that doesn't work. There's no roots. So let's just start by taking the derivative. So we're going to go n prime of x, derivative of e to the something, e to that something, so e to the negative x squared. And then we have to go inside of that power and multiply by the derivative of that. This is chain rule, so times negative 2x. And I'm going to rewrite that a little bit. Negative as negative 2x e to the negative x squared. And we want to set this equal to 0. So we have negative 2x e to the negative x squared equals 0, which means that either negative 2x is 0 or e to the negative x squared is 0. So this first factor here gives us x equals 0. The second factor, what we just saw above when we were trying to find the roots, that this has no solutions. And there's no asymptotes or anything to deal with here because we don't have a denominator. So we have a single critical point at x equals 0. And let's come up with a number to the left of this. For example, we could pick -1, and to the right, we could pick 1. So let's look at n prime of -1 is -2 times -1 times e to the -1 squared. So that's -2 times -1 is 2 times e to the negative. Now, -1 squared is just 1. So it's to the -1 because there's also that negative out in front. So 2e to the -1, which is the same as 2 over e. And that is bigger than 0. It's positive over a positive. Let's go n prime of 1. That's a -2 times 1 e to the -1 squared. And so that is -2 e to the -1, which is -2 over e, which is less than 0. So in this section, we have positive. In this section, we have negative. So we have increasing from -infinity to 0 and decreasing from 0 to infinity. And then let's figure out what our critical point is by actually just plugging 0 into our original function. So n of 0 is e to the -0 squared. So that's e to the 0, which is 1. So our critical point was when x equals 0, and we plugged that in and we got 1. So that's the coordinate 0, 1. And so that will help us graph a little bit. And now let's go on to our second derivative. So we're going to say n double prime of x equals the derivative of our first derivative. So it's the derivative of -2x e to the -x squared. And how are we going to do this? Well, this is the product of two functions, so we're going to use product rule. So we have the derivative of the first, the derivative of -2x, right? I'm splitting it like this. So it's -2 times the second plus the first, so plus -2x, right? Times the derivative of the second, so times e to the -x squared times -2x, right? In order to take the derivative of that second part, we had to do chain rule here. Okay, so let's try to simplify this a little bit. -2e to the -x squared minus, oh wait, it's actually going to be plus because I have two minuses in this factor. I have a minus right here and I have a minus right here. So those are actually going to cancel and I'm going to end up with a plus. So we're going to have plus 4x squared e to the -x squared equals 0. And let's see what I can factor out of this. I can take a 2e to the -x squared out of this. So I will have a -1 plus 2x squared equals 0. And now let's set these two things equal to 0. So we have 2e to the -x squared equals 0. Well, that would mean if I divide both sides by 2, that e to the -x squared equals 0, which we saw twice. No solutions. Over here, we have -1 plus 2x squared equals 0. Add 1 to both sides, 2x squared equals 1. So x squared equals 1 over 2. So x is plus or minus the square root of 1/2. It's important to remember that we need that plus or minus when we have x squared equals something or x to any even power equals something. With odd powers, we do not get the plus or minus. Okay, so that is going to be plus or minus √1 over √2, which is plus or minus 1 over √2. And we like to rationalize that denominator by multiplying the top and bottom by √2. So you get plus or minus √2 over 2. So if we draw our number line here, we have two roots. One of them is -√2 over 2. And one of them is √2 over 2. And so we have to pick a number in each of these intervals. So I'm going to pick 0 here. Now, notice that root 2 is definitely less than 2. So when I divide that by 2, it's going to be less than 1. So 1 is bigger than root 2 over 2. And this is symmetric, so -1 is less than negative root 2 over 2. If you weren't sure, you could just pick a number that you were sure. You could just pick a really big number. Though the bigger you pick, the harder it might be to do these basic computations with. Okay, so we're going to plug those into our second derivative. So n double prime of -1 equals 2e to the -1 squared times -1 plus 2 -1 squared. So that's 2e to the -1 times -1 plus 2. Right, -1 squared is just 1. So this gives us 2e to the -1 times 1, which is 2e to the -1, which is 2 over e. And so that's positive. So we have a positive concavity right here. So we're concave up. Let's do n double prime of 0. So that's going to be 2e to the -0 squared of -1 plus 2 0 squared. So that's 2e to the 0 times -1, right? All of this is just 0, so that's going to go away. And so that's 2 times 1 times -1, and so that is going to be -2. So we have a negative concavity in our middle interval there. And n double prime of 1 is this 2e to the -1 squared times -1 plus 2 times 1 squared. So that gives us 2e to the -1. Notice that this negative is not inside of the thing being squared. So I'm not squaring the negative. It's negative of 1 squared, not -1 in parentheses squared. Right? We can tell what we're doing based on where the parentheses are. And then that is going to be times -1 plus 2. So that's 2e to the -1 times 1, which gives us 2e to the -1, which gives us 2 over e, which is bigger than 0. And so that means that over here, once again, we have a positive concavity. And so let's write our intervals here. We have concave up from -infinity to -√2 over 2 and √2 over 2 to infinity. And we're concave down from -√2 over 2 to √2 over 2. And now I'm not sure how much interval notation you guys have used. I know they do cover it in pre-calc, but in case you guys forgot, this little U looking thing I wrote in the middle, not actually a U, it's called a union symbol. And it basically just connects two sets together. So that's just saying that it's concave up on these two different intervals. And the last thing we want to do is find the inflection points. Notice now we have 2 inflection points. So we need to plug our, I guess you could call them inflection numbers, which are -√2 over 2 and √2 over 2 into our original function. So let's do that. Okay, so let's find n of -√2 over 2. And that is going to be e to the -√2 over 2 squared. So that's e to the negative, and then -√2 over 2 squared is 2 over 4. And that negative outside stays. So that's e to the -1/2, which is 1 over e to the 1/2, which is 1 over √e. And now you could ask, oh, well, shouldn't I rationalize the denominator so that I get something like we did before and we had 1 over √2? And the answer is no, probably not, because when we had 1 over √2, we could fix it by turning the denominator into a 2. And so it started as irrational and then it became rational. In this case, we have 1 over root e. And then if I did the same thing here and replaced 2 by e, then I would end up with, so I could say that this equals root e over e, but the denominator is still irrational because e is irrational. So this, and I think that this looks more complicated, so that's not better, in my opinion. And it certainly isn't rationalizing the denominator. So we're just going to leave it like that. And then let's do the other one. N of root 2 over 2 equals e to the negative root 2 over 2 squared. And I think we can see that this is going to be the same thing. So that's e to the negative 2 over 4. And then following what we have above, we see that that is equal to 1 over e as well. So we can say that our inflection points are negative root 2 over 2, comma 1 over root e, and root 2 over 2, 1 over root e. So now let's do one more thing that I think will be helpful before we graph. It's helpful to go through all the things that we found when we were graphing rational functions and see if any of them will be easy to compute. Just like we found roots, asymptotes. In some cases, end behavior can be a little bit confusing if we have functions that aren't polynomials, but in this case, I think it's not going to be too bad because if we take the limit as x approaches infinity of n of x, which is the limit as x approaches infinity of e to the negative x squared, and I can rewrite e to the negative x squared as 1 over e to the x squared, and I can say that that in some sense equals 1 over e to the, I'm going to say, big number squared, right? Because that is our x that's approaching infinity. And so that's 1 over e to big number squared is big number. And then 1 over e to big number is 1 over big number. And that is going to approach 0. And for negative infinity, we have essentially the same thing. So limit as x approaches negative infinity of n of x equals, and I'm just going to skip to that third step there that we have above, which is negative infinity of 1 over e to the x squared. And so that equals 1 over e to the negative big number squared. But when we square a negative, it becomes positive. So that becomes e to the big number. And then just like as above, we say that that goes to 0, right? Because we just get this really big number in the denominator, right? And we think of that thing where I wrote big as a number that's just getting bigger and bigger and bigger. So we are approaching 0. So our end behavior approaches 0 in both directions, which means that we have a horizontal asymptote at right on the x-axis at y equals 0. So let's try to graph this. And so we know that we have a critical point. Let's go back up here and remember everything that we said. So we said that we're increasing. So this entire range, we're increasing from negative infinity to 0. And over here, we're decreasing. And we have a critical point here at 0, 1. So I'm going to graph that right here. And then let's look at our second derivative things. So we said that we are concave up until negative root 2 over 2. So let's add those points in here too. Negative root 2 over 2 and root 2 over 2. And so from this concave up, here we're concave up as well. And then in this interval from negative root 2 over 2 to root 2 over 2 is where we're concave down. And then we will also try to graph our inflection points. Notice that 1 over root e is certainly less than 1 because e is bigger than 1, root e is still bigger than 1. And so we'll just kind of plot our points somewhere like this, and we'll just label those points as root 2 over 2, 1 over root e, and negative root 2 over 2, comma, 1 over root e. And now let's try to graph this. So we know that we have this asymptote over here on the x-axis. We also know that there's no roots, so we can never cross the x-axis. And since we're positive on the points we drew, that means that we are approaching the x-axis from the top. So we are going to go kind of like this. And we're also concave up all the way up through here. So it looks like this, but then we have to be concave down in between until we hit this other inflection point, and then we become concave up again. And we look like this. Great. And so this is our function n of x. And it is called n of x because this is the function that defines the shape of a normal distribution in statistics. So now we're going to talk about partial fraction decomposition. In the past, you might have learned like a lot of different rules for this and like all these special cases. There really is a single rule that you need to know, and it's this. If the degree of the numerator is greater than the degree of the denominator, you start by doing polynomial long division. Then you'll be left with a fraction that has a numerator with a smaller degree than the denominator. So either way, you end up with a numerator with a smaller degree. And then for each ax to the n plus blah, 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 all to the n in the denominator, you're going to add terms of the form. And then so we have a numerator that has a degree 1 less than the denominator. See, we're starting with x to the n minus 1 over that thing in the denominator, that ax to the n plus blah, blah, blah to the k, for every k that's less than or equal to n. Okay. Now, and that's kind of a mouthful. We're going to look at this example here. So we're going to start. So we have 3x to the 12 minus x squared plus 7 over x to the 5th plus 10x to the 4th plus 15x cubed plus 15x squared minus 10x plus 3, all cubed. And the assumption that we need to make, first of all, is that these terms are irreducible. So that's important. This quintic equation that we have written here, we can't factor that. That's what irreducible means. It means that we can't factor it. So that means that we're fine to go ahead. So we're going to write this general quartic in the numerator. So that has 1 degree less. And so we just put all the terms there and we leave, by convention, capital variables as the coefficients. And then every power less than 3 of that denominator, we're going to have in these denominators. But all of these numerators only go up to the 4th power, even though technically this last one has a 15th power in the denominator. The power of the numerator is just based on that thing inside of the parentheses. Right, so originally we have a numerator in the 12th power, denominator 15th power, and that's why we didn't have to start with polynomial long division. Okay, that example is worse than anything you're going to have to do, but I just think it's quite illustrative of exactly what the rule is. Because if you understand this, it basically encapsulates everything that you have to know about partial fraction decomposition, at least in terms of setting up the problem. But so let's do an example that's a little bit more manageable. So let's say, for example, we have this. So we notice that the numerator has a degree that is 1 less than the denominator. So we don't have to do partial fraction decomposition because it's not higher degree numerator. And first thing we want to do is factor the denominator as far as we possibly can. So we want all of the factors to be irreducible. So we're going to say that this is 4x squared plus 3x plus 2. Notice that I'm not factoring the numerator. We don't want to factor the numerator when we do partial fraction decomposition. So that is x squared, and then I get an x plus 1 here. And that's certainly as far as I can go. So now how are we going to set this up? So we have an x squared, and so we're going to think about all the powers of x that are less than 2 are going to go on the bottom, less than or equal to 2. So we get an x and an x squared. And since this is just an x, which is an x to the 1st, we're going to go 1 degree less than that on the top. So it's essentially x to the 0, which is a constant. So we put a in the top, b over here, are just constants. And notice that whenever I need a constant or a coefficient, I basically am just moving through the alphabet. And then our other term is x plus 1. So we're going to get an x plus 1 in the bottom, and we only have one of those because that already just has degree 1. So we're going to put a c over here because, once again, that's a linear denominator, so we get a constant numerator. Okay, now typically our goal in these problems is to calculate what a, b, and c are so that we can rewrite our original fraction as a simpler sum of fractions like this. So quick diversion. Let's just talk about adding fractions really quick. So let's say that I wanted to add, let's say 1/12 plus 1/8. Okay, what do I need to do here? Should I just multiply the one on the left by 8 and the one on the right by 12 in the top and bottom? I could, but it's going to be more complicated than I need to because we're going to end up having a pretty large denominator. And we're going to see that in our case, when we have these variables, if we do always just try to multiply by everything else, it's going to get very unwieldy, and we're going to end up with things that we don't even know how to factor. So we don't want to do that. We want to say, what is the greatest common multiple of 12 and 8? And so that's actually 48, right? I can say, well, let me multiply the top and bottom of this one by 4. And let me multiply the top and bottom of this one by 6. And that's all that I have to do. So then I get 4 over 48 plus 6 over 48. So that gives me 10 over 48, which I could rewrite as 5 over 24. Okay. And so keeping that in mind, let's think about what we need to do in order to get a like denominator between my a, b, and c if I were to add these together. Well, what's essentially our goal denominator? Well, this is even easier than with numbers because what we have over here, this is our essentially goal denominator. So we just have to think, what do I have to multiply my x by to get x squared x plus 1? Well, I have to multiply it by x times x plus 1 because that's all that's missing in the denominator. What about from this second one? That denominator is only missing an x plus 1, so we're going to multiply the top and bottom by x plus 1. And this last one is missing an x squared. Okay, so now let's try to write this a little bit straighter. So I have a times x squared plus x plus bx plus b plus cx squared over x squared times x plus 1 equals, and then let's copy this numerator. So that equals 4x squared plus 3x plus 2 over x squared plus x plus 1. Notice that we have the same denominators. So if these things are equal, their numerators must be equal too. So I'm just going to finish kind of expanding my numerator on the left. So I have ax squared plus ax plus bx plus b plus cx squared equals 4x squared plus 3x plus 2. Then I'm going to group all of these things together. So I have ax squared plus cx squared. So that's all my x squareds plus ax plus bx plus b. And then I'm going to factor my x squareds out, or my all my powers of x out. So I have a plus c x squared plus a plus b x plus b equals 4x squared plus 3x plus 2. Okay. Now, what do I know about all of these things? So these are the same, and they're the same for every x, which means that these are actually the same polynomial. So on the right, I have a 4 in front of my x squared, so a plus c is 4. I have a plus b in front of my x on the left, and on the right, that's a 3, so that has to be a 3. And my constant is a 2, so I know that b is 2. Okay. So now we're trying to solve for all of these things. So let's just write starting with this, b equals 2. Okay, now I know that a plus b equals 3. So we have a plus 2 equals 3. So that says that a equals 1. Okay, and then I have a plus c equals 4. So 1 plus c equals 4. So c equals 3. So now I have that my original fraction, my original rational function, we said is a over x plus b over x squared plus c over x plus 1. And so now I'm just going to replace my a, b, and c with what I found them to be. So that's 1 over x plus 2 over x squared plus 3 over x plus 1. And so essentially that is our final answer in terms of just performing the partial fraction decomposition. Now I understand that this at this point looks a little bit unmotivated. It's like, why are we even doing this? The reason that we're doing this is because later it's going to help us with integration. But since this is a pre-calculus technique, we're going over the technique now so that we'll be ready to use it later when we need it. Here's one last example, and we're going to notice that we start with a numerator that has a higher degree than the denominator. So that means that we have to do polynomial long division. So we're saying how many times does x squared plus x minus 2 go into x cubed minus x plus 4? And notice I left a blank because I want to include all the terms. So I'm just going to say plus 0x squared right here. Okay. Now, the way we do this is we're just going to look at this x squared and this x cubed. We're going to say how many times does x squared go into x cubed? What do I have to multiply x squared by to get x cubed? Well, I have to multiply that by x. So then we go and we multiply this first equation by that x. So we're multiplying everything. So that gives me x cubed plus x squared minus 2x. And then we subtract. I see people make this mistake so much, is that they maybe even write the subtraction sign and then they don't subtract, they add. So this is negative x minus negative 2. So that's minus x plus 2, and that is x, positive x. Okay, 0x minus positive x squared. Right, we're subtracting everything in here. So that is minus x squared and then x cubed minus x cubed. If we did everything right, that first term should be 0, and by convention, we don't write it. Okay, so we subtracted. We're going to pull down one more term. In this case, it's our last term. We're going to say how many times does my x squared go into, once again, this first term here, and that is negative 1. I'm going to put negative 1 above it up on top. I'm going to multiply by whole thing by negative 1. So negative x squared minus x plus 2. Once again, we are subtracting. So 4 minus 2 is 2. X minus negative x is 2x. And this first term is 0. Okay. And now we say how many times does x squared go into 2x? I can't multiply it by any polynomial to get that. So we're done, and we have a remainder of 2x plus 2. Okay, so this function here equals x minus 1 plus 2x plus 2 over x squared plus x minus 2. We can verify here on Desmos that we did it right. So this here is our original function, and then this is how we rewrote it, and we see that those line up perfectly. So those are the same thing. And now what we want to do is notice that once we do polynomial long division, now we'll always have a degree smaller than the numerator in our fractional part. And so we're going to go ahead and factor the denominator. So 2x plus 2. I'm just ignoring everything that isn't in the fraction for now, but we have to remember to include it in our final answer. So 2x plus 2 over x plus 2, x minus 1. Okay, so that's going to be our denominators. Just have one each, one of x plus 2, and one of x minus 1, since the power is 1, so we just get one of these, and we get constants in the top. And so let's see what we need to do. So to this first one, we need to multiply top and bottom by x minus 1, and to the other one, we need to multiply top and bottom by x plus 2. And I'm going to kind of write this without doing the work on the bottom, just so you can get in the habit of thinking about it this way, because this is really the fastest way to do it. So I'm just going to say a times x minus 1 plus b times x plus 2. I'm just thinking about what's going on in the numerators, and I'm just ignoring the denominators, equals 2x plus 2. And then we just go and expand it like before. So ax minus a plus bx plus 2b equals 2x plus 2. I'm going to move those x's together, ax plus bx minus a plus 2b equals 2x plus 2. And so I have a plus b x. We could say plus negative a plus 2b equals 2x plus 2. And so we know that this right here is equal to 2, and this right here is also equal to 2. So one common technique here is to go a plus b equals 2, and then negative a plus 2b equals 2. I'm writing them on top of each other. And then I'm going to add these equations together. So over here we get a 4. Over here we get a 3b. And over here we get nothing. So this actually worked out really nicely in that one of them already canceled. But kind of suppose these a's didn't cancel. And like, let's say we just had negative a plus 2b. And suppose, for example, we wanted to cancel the b's out for whatever reason first. Well, then I could take, so I have this a plus b. And in order to cancel those b's, I need that b to be negative 2b. So I'd multiply this whole thing by negative 2. And then that's going to give me, so then I'd have a plus 2b on top. Then I'd have negative 2a minus 2b. And actually, I should make sure I'm including that equal sign inside of what I'm multiplying. So it's going to equal negative 4. And this is going to be 2. So I would get negative 3a equals negative 2, right? Those b's are going to cancel right out. And so then I get a equals 2 over 3, right? It's really negative 2 over negative 3, but the negatives cancel, so I get 2/3. And then over here, before we just finished this, I get b is 4/3. And let's just make sure everything, let's just sanity check that both of these approaches would give us the same result. So if I was just doing this approach on the left and I said b is 4/3, then I could go use, I could use either of these. So let's just say that I have this thing where I have a plus b equals 2. Then I have a plus 4/3 is 2, which is 6/3. And so I'll subtract 4/3 from both sides. I get a is 2/3. Or if I went over here, right, we could use, actually, let's just use the other one just to show that they both work. We have negative a plus 2b equals 2. So negative 2/3 plus 2b equals 6/3. So 2b equals 8/3, or b equals 4/3, just like we originally found on the left side. So either of those work. And so then our final answer is going to be that x cubed minus x plus 4 over x squared, what was it again? It was x squared plus x minus 2 equals, and then we can't forget our first part, so that's x minus 1. And then so we have it's plus this fraction here, and we said that fraction is a over x plus 2, so it's plus 2/3 over x plus 2 plus 4/3 over x minus 1. Yep, that looks good. And so that's going to be our final answer for this one. All right, and we're going to end there for today, and we will see you next time in our lecture on optimization.